So here we can write from induction hypothesis, the center of T prime is a vertex or an edge. Okay. Now what we have to show to prove that indeed the center of T prime is indeed the center of T also. Okay, so the center of T prime is a vertex or an edge. That is the first step we prove. Second step we prove that if the same vertex and the same edge, which is the center of T prime, will also be a center of T. That is something we have to prove. Okay. So to prove that, what we do, so since the internal vertices on paths, we know that for given two vertices, there is one and only one path. Since the internal vertices on the paths between leaves of T remain same, it's mean T prime has at least one vertex. Why that is so? Because here our value of n is greater than equal to 3. This value of n is greater than equal to, so if it has at least 3 vertices, I know that at least there are 2 leaves on the two end of the path. So there is at least one internal vertex. So that is, so T prime has at least one internal vertex. Okay. Now what happened? Every vertex at minimum distance in T from a given vertex U belongs to Vt is a leaf. So basically, in this tree T, if you choose any vertex, suppose in this tree U is one vertex, so the maximum, every vertex at maximum distance from U, they must be leaf. Okay, so 5 is at maximum distance, it must be leaf. 4 is at a maximum distance, so that is also in leaf. So every vertex at maximum distance in T, so maximum distance कौन सा है यहाँ पे in this graph? 1 2 3 and 4. So maximum distance में ये U का maximum distance है vertex 5, and that must be a leaf. Otherwise, the path reaching from U can be extended further. Okay. In that case, it is not a maximum distance. So from given any vertex in T, the vertex which is at maximum distance from it is basically a leaf. Since all the leaves have been removed from T to get T prime, and once I remove this leaves, what happened? The T prime is again a connected thing. So that is also a tree. And no path between the two other vertices uses a leaf. So in T, what are the things? In T, we have removed the leaves, green leaves. So they are being removed. But we know that once we remove them, it doesn't disconnect the tree. So every path remain intact. Okay. And because every path never uses leaf as its internal node. Okay. So since these are two cases, so we can say that the eccentricity of a vertex U in T prime is nothing but the same vertex eccentricity minus 1. Okay. So why it is so? Suppose you take U. In the original tree, its eccentricity was 4, right? 1, 2, 3, and 4. Okay. Now, U's eccentricity is 4. And now what happened? If I So why it's 4? Because the vertex at longest distance is at distance 4. So it is 1, 2, 3, and 4. Now, since the maximum path is a leaf, if I delete this, since this is a leaf, I delete it, so the eccentricity got reduced by 1 in T prime. So that is happened. That is why it is Yuka eccentricity in the new system is 3. So E T prime U, the vertex eccentricity in T prime is equal to its original eccentricity minus 1. And it is true for all the vertices in T prime. Also, the eccentricity of a leaf in T is greater than the eccentricity of its neighbor in T. That is very natural. Okay. कि इसमें लीफ का eccentricity highest होंगे. So the eccentricity of a leaf T is greater than the eccentricity of its neighbor. So कोई भी leaf ले लो, इसका neighbor से इसका eccentricity ज्यादा ही होगा. Because neighbor का जितना eccentricity होगा, if we do a +1, you will get the eccentricity of the leaf in most of the cases. Okay. So hence, what happens? The vertices that minimizes this eccentricity of U in the original T are same as the vertices minimizing eccentricity of U in T prime. Okay. So T and T prime have the same center. And by induction hypothesis, we knew that T prime is the center of T prime is either a vertex or an edge. So basically, center of T equal to center of T prime. And from induction hypothesis, we know that that center of T prime is a vertex or an edge. That is clear from the induction hypothesis. So basically, what happens here? Basically, the proof is like this. If you have a single vertex, that is itself a center. If it is an edge, it is itself a center. That's all. Now we have to prove it for, and we claim that induction hypothesis that if number of vertices is less than m, then it is the claim is true. And we have to prove it if the number of vertices is equal to m. How have we proved it? So we create a tree T prime by deleting all the leaves, and by induction hypothesis, I know that T prime, the center of T prime must be a vertex or an edge. Now the thing that remains to prove is the center of T is equal to the center of T prime. And the logic behind this is that for any two vertices in T, there is a one and only one path, and its extreme vertices are the leaves. So if I delete them, if I delete the vertices, the internal vertices in T prime, the internal vertices in T remains the same vertices as T prime. And not only that, the eccentricity that is of any vertex U in T is reduced by 1 in T prime. Okay. And the reason for this eccentricity is the same set of internal vertices. Okay. So the eccentricity of a leaf in T is greater than the eccentricity of its neighbor in T. Hence, the vertices that minimizes eccentricity of U in T are identical to the vertices that minimizing the eccentricity of U in T prime. So they have the T and T prime have the same center. Okay. Now, so this is the T, and if I delete the vertices, I get this T prime. So T prime का फिर इसका जो leaf है इसको मैं delete कर दूंगा. Now it becomes 1. So one single vertex is its eccentricity. So if you look into the theorem and somebody asks you to find the center of the graph, so from any graph, not for any graph, sorry, for any tree, if somebody asks you to find out the center, so the thing is you keep on deleting the, no, it is not the right idea to do this algorithm. Like there are much better algorithm for this, to find the eccentricity and then find the eccentricity, find those vertices having the same eccentricity, same minimum eccentricity. So in other words, you delete all the leaves here, followed by you again delete its leaves. Then you get a single vertex, and you know that this single vertex will be the center of this tree. Now this is a spanning tree property. So it is given that suppose T and T prime are spanning trees of a connected graph G. Look here, it is not a minimum spanning tree. What they say is that T and T prime are two spanning trees of the same connected graph G. And suppose E belongs to T and E doesn't belong to T prime. So E belongs to T, the edges in T, but it doesn't belong to T prime. Then the claim is there is always an edge E prime which belongs in T prime and not in T, such that T minus E plus E prime is a spanning tree of G. Okay. So basically it gives another spanning tree. So you are given two spanning tree of the same graph G. Now we can construct another spanning tree by this, which is T minus E plus E prime. So what happens? So suppose you have the spanning tree. Now it is a tree, that means if it has n edges, then it is n vertices, then it has n minus 1 edges. Now out of them you choose any vertex E. Now if you delete that E from the spanning tree T, what happens? It will create more than one component because every edge is a cut edge. Okay. Now you get two components after this step. And what is E prime? So E prime is another edge which exists in T prime but not in T. Okay. So once you remove T, you get two components. Now among those two components, you can select some edge E prime such that which belongs to T prime and not in T. So what happened? It will again be connected. So here the statement is, since every edge is a cut edge in a tree, deleting E from tree creates two components, U and U prime. Since T prime is connected, that means T prime is another spanning tree. Since T prime is connected, then T prime has an edge E prime with endpoints U and U prime. Now T minus E plus E prime is again connected and having n minus 1 edges. So it must be a spanning tree. It's very trivial proof. Then there is another proof where it says that T plus E minus E prime is a spanning tree with the same statement. Okay. So suppose T prime is a spanning tree. So if I add an edge, it will create a unique cycle in C. Okay. Because why? Because T prime. So if you add the edge E, its two endpoints have a so suppose this E has two endpoints A and B. Now in T prime there is exactly one path from A to B, and along with that edge AB, it gives you a unique cycle. Now since the graph T, that is another spanning which is acyclic, we know that we can always find an edge in this cycle which we can remove. Okay, and if I remove that, it will break the only cycle in T prime plus E. So now T prime plus E minus E prime is again connected, and since it is acyclic, so from these two definition I know that it is a spanning tree. Okay, so that is the property of spanning tree. Now a very interesting thing is called Calais formula. So today we won't go to the proof of Calais formula. Today we will learn the algorithms, how so why Calais formula is interesting and how it helps us to encode a spanning. So basically today we will study the encoding of a spanning tree having n vertices. Okay, so we don't go into this slide. We will look it in the next class. Okay, and okay, now what is the application? Suppose somebody gives you a, for every spanning tree with n vertices, where each vertex is level, so where each of the vertices level from either 1 to n can be uniquely mapped to a proofer code. Okay, so what is a proofer code? We will look into it. Okay, so n vertex ko leke, so what Callis formula tells that if you have n vertices level from 1 to n, you have n to the power n minus 2 spanning trees. Okay, so that is the formula of Callis formula, which we will prove in the next class. Okay, and for a set S of n numbers, we know that there are exactly n to the power n minus 2 ways to form a list of length n minus 2. Okay, suppose you are given n different numbers and and somebody asks you to create a set of n minus 2 numbers where repetition is also allowed. So out of this n number, first number can be taken in n ways, second number can be repeated another n ways, and n minus 2th number can be taken is again n ways. N to the power n minus 2 ways to form a list of length n minus 2. And each entry, so this n, so each of this n to the power n minus 2 entries is called a proofer code. Why? Because for each of the representation, we can create an unique spanning tree out of it. Okay, how from a proofer code we can create a spanning tree, or how from a spanning tree we create a proofer code, we will see it shortly. And why it is needed? So suppose somebody asks you to send some tree data, structure from sender to receiver end, and it is a communication network. There are two ways you can send. You can send the data structure itself, so where it mentioned that what is the adjacency list of each of the vertices. That is one possibility. Another possibility is a compact representation. You just send, instead of sending a graph, or you are sending a graph or tree having lot of pointers, instead of it, if you send a simple proofer code, which is nothing but a set of numbers, set of n minus 2 numbers, then what sender will do from the spanning tree, he will create a proofer code, and proofer code is a set of numbers that can be easily be transmitted over the link to the receiver. Once receiver get the proofer code, he can uniquely construct, or should they uniquely reconstruct the original spanning tree. Okay, so now we see that how from a spanning tree a proofer code is created. So this is a spanning tree of 8 vertices, and these are the vertex number 1, 2, 3, 4, 5, 6, 7, and 8. Okay, now our objective is how to represent this spanning tree as a proofer code of n minus 2 numbers. So there are, here n is 8, there are 8 vertices, so 6 numbers I need to create. So I need to create a list of 6 numbers which actually uniquely represent this tree. How do we do this? The algorithm says, given this tree, you find the leaf having minimum vertex number. So leaf is this 2, 6, 8, 5, and 3. Amongst them, the minimum vertex number is 2. So what we do, we will delete 2, and we will uh, jot down its neighbors name. So what I do, out of the leaf, I find which vertex has the lowest, which vertex has the so which vertex has the minimum level. So 2 is the minimum. So leaf with minimum number is 2. So delete leaf number 2. So you delete it, you get this graph. Append 7 to proofer code. So 2 ka jo neighbor hai, that is 7. So that is included in the proofer code. That's all. Now you repeat this step again. For this tree, what is the minimum number? That is 3. So you delete it. and you jot down 4. So earlier it was 7, 7 के बाद आ गया 4. Okay. Okay. So now for this graph, what is the minimum leaf number? That is 5. So you delete it and you note its neighbor, that is 4. So 7 4 था already, और भी 4 add हो गया, 7 4 4. Okay. Now in this graph, which is the minimum leaf? 4. So I will delete it and I will report its neighbor in the proof of code. So 1 is the number. So 1 will 744 is earlier there. So 7441. So I delete it. Now this is the graph. What is the minimum number? That is 6. So its neighbor is 7. 7 will be noted. So 7441 was there. Now 74417 is there. 74417. And you delete this edge. In this graph, what is the minimum number? 7 is the minimum number and its neighbor is 1. So earlier it was 74417. Now 1 is appended. Now when you have a single edge, you don't do anything. Okay. So 744171. So basically what I am trying to say here, that instead of sending this spanning tree, you send its proofer code of length 6. Since it has 8 vertices, its proofer code should have the side 8 minus 2, that is 6. And what is the proofer code? The proofer code for that graph is 744171. Now instead of sending the graph, if I send this number 744171, the receiver can reconstruct this spanning tree. So if somebody give you 744171, then the receiver can reconstruct this spanning tree. Now we will see how we will do it. Okay. Basically, what we should do, so you know that my original proofer code is 74417. So this is done by the receiver end. Okay. So transmitter, what it does, given a tree, it convert it to proofer code, and proofer code is sent over the internet. Now the receiver received this proofer code and his task is to reconstruct the spanning tree. Now what the receiver will first do, it first checks how many entries are there. So there are 6 entries. So it understands that the graph has, if its entry is n, there is n plus 2 vertices, so 8. So there are 6 entries in the list, so 8 will be the number of vertices. And he labeled them like 1, 2, 3, 4, 5, 6, 7, 8. That is the first task he will do. Okay. Next is it has to create the edges among them. So the algorithm is the initially unmarked vertices are all 1, 2, 3, 4, 5, 6, 7, 8. Now first number in the proofer code is 7. Okay. 7. Now you have to find what is the minimum unmarked number which is not there in the proofer code. I will repeat. So basically so proofer code has length 6. So I know that I have 8 vertices and they are labeled 1 through 8. Initially all the vertices are unvisited or unmarked. Okay. And you know that the first number in the proofer code is 7. Now my question is 7, with whom 7 should be paired up? So 7 should be paired up with that vertex which is first of all unmarked and which is not in the proofer code. So 1 is unmarked, but 1 is there in the proofer code, so I cannot choose it. 2 is unmarked, but 2 is not there in the proofer code. So minimum unmarked number which is not there in the proofer code is 2. So 7 के साथ 2 एक 8 से associated होगा, 2 7 will be connected, and once that is done, now 2 became marked, so you delete 2 from this list. So in the next list you see that 1 3 4 5 6 7 8, 2 is deleted and 7 is also deleted from proofer code. Next item is 4. Okay, 4. Then what is the minimum unmarked number that is not in the proofer code? Okay, one is unmarked, but one is there in the proofer code. 3 is unmarked and 3 is not there in the proofer code. So 3 is the right candidate. So with 4, vertex 4, 3 will be paired up. So 4, 3 is paired up. Then you delete this 4 and delete this 3 also. If you delete 4, it is 4171, and delete 3 from here, it is 145678. Now the first number is 4, the proofer code, and the unmarked vertices, which is not there in the proofer. 1 is unmarked, but it is in the proofer code. 4 is unmarked, but this is in the proofer code. 5 is unmarked, but 5 is not in the proofer code. So 4 के साथ 5 का pair up होगा. So 4 and 5 is paired up. Then what we do, we delete this 4, so it turns out to be 171, and we delete this 5, so unmarked vertices will be 14678. Okay, this is 14678 and 4 is deleted, so it turns out to be 171. Now with 1 it should be associate, 1 will be associated to 4 because 4 is the first unmarked vertices which is not there in the proofer code. So 1 4 is associated. Again I delete 4 and I delete 1. Okay, I delete 4 and delete 1, so it becomes 71. If I delete 4, it was 678. Now 7, the vertex 7, that is in the top of the, it should be associated with some vertices. Which vertex? Which is an unmarked vertex. At the same time, it is not in the proofer. 1, it is unmarked, but that is there in the proofer code, 71. 6 is unmarked, but that is not there in the proofer code. So 6 is the right candidate to be paired with 7. So 6, 7 is paired up. Okay, then 6 is removed and 7 is removed. So proofer code is 1 and the unmarked vertex is 178. So this vertex 1 should be paired with that unmarked vertex which is not there in the proofer code. So 1 is there in the proofer code, so it won't be associated. 7 is not in the proofer code, so 1 7 will be connected. So this 1 7 will be connected. Now you delete this. So now proofer code is null and you have two vertices 1 and 8 left. Since two vertices are left, you add them by an edge. So 1 8 is left, so you add them by edge. You originally construct the spanning tree. So in the next class we will prove Calais theorem and we'll discuss few more algorithms. Okay, so today I end my lecture here itself, and okay, so okay, let's see. So yeah, if you have any question on this, you can ask me. So basically the good part about proofer code is given any spanning tree where the vertex numbers are represented as 1 through n, you can always create an equivalent proofer code of length n minus 2 for it, and you can send it over the net. It will consume less bandwidth. Okay, so right now it is all the works what we are doing. Most of the cases we encounter cases where the amount of bits that need to be transferred across the net should be minimum to reduce the load, overall load. So this is a kind of coding technique. So given a tree, you can code it with few numbers, and it is easier to transmit a number over the net rather than sending any complicated structure. So that is the benefit. Not only that you here you will prove that for every unique combination of n minus 2 numbers, there is a one and only one spanning tree. Okay, so that is the Calais formula, and Calais proves that such kind. So there are n to the power n minus 2 cases are there. Okay, so thank you. With this I end today's class.